Hello, everyone. I'm Vincent Santiago for the National Institute for Space Research in Brazil, and I'm going to present this work. A method and experiment to evaluate deep neural networks as test oracles for scientific software. Scientific software usually produce non-trivial outputs such as 2D, 3D image or plots. Testing such kind of systems is not straightforward. They usually behave non-deterministically, produce such non-trivial outputs, and also test automation, particularly test oracle, is not easy either. Some examples below, when we show here some CT scan medicine software, environmental modeling outputs, and social biological modeling related to the pandemic is COVID-19. There are several prior studies that basically rely on the output of the software systems, the image, and try to detect bugs in the scientific code and scientific models. The studies use techniques like image processing, computational vision techniques, machine learning, ML, deep learning, DL. One of the reasons for the success of artificial intelligence are the deep neural networks, and particularly deep convolutional neural networks, which are still the most popular techniques even today. These networks basically will have a set of layers that altogether do all the process starting from the feature extraction of the image up to the classification, correct classification of the image or object detection. So you can think that this type of techniques can help in our test oracle problem. However, several recent studies show that popular CNN models can indeed misclassify thousands of images, particularly corner case behaviors. These previous studies basically use the image dataset for autonomous cars in classical benchmark, ImageNet, COCO, CFA, and NIST. None of these datasets were composed of images derived by scientific software, such as environmental models and plots of social biological models. The contributions of this study will propose test oracles based on CNNs to test scientific software. We address two types of outputs, cellular space, and plots. We propose a method, test oracle based on CNN, TOrC, that starts by the generation of training, validation, and test image datasets by combinatorial interaction testing applied to the original codes and second-order mutants. We accomplished a thorough investigation, and we also propose a new technique, feature and neighborhood-based analysis, FNA, to explain the image misclassifications. The context of our method that we use it to develop our method is that a scientific team has some experience with machine learning and wishes to start working with deep learning to support the software testing activity. This is the general view of our method, the TOrC method. We start by the oracle information generation, part of the test oracle, and we use the combinatorial interaction testing algorithm, and the tuples generated by the CIT algorithm are then applied to the correct code in the mutant code. So we get these tuples and overload the values of parameters of the scientific model, and after some time, simulation time, we generate the image. So these are applied to the correct codes and second-order mutants. Our remark is that this is a binary classification problem, okay? Correct class, pass, and mutant class, fail. After that, we have the select data task, which split the image into the training and validation sets. In order to do this, we generate a rank based on image similarity metrics, where we get more dissimilar images. Based on image similarity metrics, we got images that are more dissimilar in order to have more significant datasets. Data augmentation is a well-known technique that people use with deep neural networks. The idea of the motivation is to decrease the errors, image misclassifications due to the ML models by reducing overfitting. We do it only for the training set. Example here of our original image on the left, and on the right, a data augmented image with two transformations, horizontal flip plus cutout transformations. This is an example of a cellular space image, and this is a fire spread model. In red, we have part of a forest which is burning, and right, part of the forest which is intact. The CNN is the Oracle procedure, so we're responsible for assigning the pass-fail verdicts. We use transfer learning, also known technique, with pre-trained models, where we start the training of the networks with the velocity parameters not from scratch, but the values are loaded from pre-trained models. And the approach is fine tuning the CNN. For the inference phase, the test set is created based on the output of programs completely different from the ones used to create the training and validation sets. This is very important because, of course, we want that our technique, our method is general enough. So in the real life, this method will see images that are were generated by completely different source code, scientific code. So you want that this method is general enough. The CNN assign the pass-fail verdicts, and we have as a last step the evaluation of the classification. This is precisely the motivation to develop the FNA technique. MLDL models classifying images incorrectly is a huge problem today. There are several examples in the literature, in the media, showing problems with autonomous cars, applications that incorrectly classify people. This can cause some problems for certain social groups. So there is a very interesting subfield of artificial intelligence today called explainable AI. The idea behind explainable AI is that it is not enough just to produce better ML systems. We may try to explain why these models fail. This is the goal of the FNA technique. This is a straightforward and black box approach, rely only on the image of the training and test sets. FNA is based on the k-nearest neighbors, KNN ML algorithm, where the idea of KNN is precisely make some analysis, considering which are the neighbors of a certain element of the set, now the set element of the data sets, image data sets. Briefly speaking, as for FNA, we define 6 classes, different from the class mutant correct. So, for instance, TOrC means that this image is from the correct class of the training set. MI-core means that this is an image of the correct class of the test set, but which was misclassified by the CNN. So in this case, we have the 6 class that help the technique to explain the misclassifications. One important feature of our technique is providing an exact form manner to calculate the number of neighbors in the KNN algorithm. And here is the idea is use the rate of T divided by S, where T is the number of images of the training set, and S the number of images of the test set. And the idea is here to get the number of nearest neighbors for each image IS of test set, where each image IS is viewed as a centroid of a cluster. At the end, we have a matrix with the values of the class, which got the higher proportion for each image IS of the test set, the matrix P. To explain the error, we just look at P and see whether it matches the logic of nearest neighbors. So if an image of the correct class of the test set was misclassified, MI-core, we would expect that the corresponding element in P is TR mut. Why? Because of the fact that we have more images of the mutant class of the training set, explain why this network failed to correctly classify this image. We have 4 questions to answer. The first question is that, does a deeper CNN, more layers, always have better performance compared to a CNN with less layer? Because when people start working with deep neural networks, deep learning, the one first thought is that, okay, as much layer better for me. But we would like to realize if this is true in our case. The second question is that, if we do not change the architecture of a predefined model network, is transfer learning able to get the same or better performances compared to extended architectures of the model? Because this is another thing that we see a lot when reading about deep neural networks, deep learning. People talk very good about transfer learning, and this is a very interesting technique. But we want to see that this transfer learning in our context is good enough in very challenging situations with images very different from the ones used precisely to pre-train the models. There is a recent paradigm in the artificial intelligence community called data-centric AI. Basically, the idea of this paradigm is that put more emphasis in data engineering, the pre-processed step of deep learning, rather than trying to evolve models. We can do it, can still do it, but put more emphasis on data engineering. We want to see if this is an interesting path to follow. And last, we want to realize if there is a correlation between the software bugs in the scientific models and the errors presented by the CNNs. If somehow the bugs, the mutant code, influenced the CNN so that this is the cause to explain why the CNNs failed. All data sets, code, and extra information you can see here in this GitHub page, of course, in addition to the paper itself. For scientific models, we use the Terra-ME, a multi-paradigm modeling toolkit that we develop here in our institute. For the second order mutants, for the training validation datasets, we use these operations AOR1, 3, 4, ROR1, 2, 4, and 5. And for the test dataset, conditional COR, AOR1, 2, 3, 4, ROR1, 2, and 5. To create the datasets, we use the tuple relocation city algorithm that we presented some time ago. Structure similarity to create the free sets with the full limit of 0.85, all the other limits were used, and the transformations related to data augmentation with horizontal flip, rotation 10 degrees, horizontal flip plus cutout, and change the brightness. We show here 2 plots derived by susceptible, infected, and recovered SIM model. The ideas of the model are still very useful to model pandemics like COVID-19. On the left, we have an image generated by a cohort model. On the right, we have an image generated by a mutant model. In order to answer question 3, we developed 2 dataset profiles, totally similar TD, where we have 2,688 images in the training set, 160 images in the validation set, and 160 images in the test set. For some similarity profile, we reuse all the previous images, but we added 160 images created by the test set related codes. But it's very important to mention that these new extra images will completely different from the image considered for the test set. I mean, these new 160 images are completely different from these other 160 images. We used 7 CNNs, starting with HasNet 18 with 18 layers, and going up to DenseNet 161 with 161 layers, right? Here we have HasNet 34 with 34, HasNet 50, 50 layers, wide HasNet 50 with 50 layers, Inception with 3, 48 layers, HasNet 152, 152 layers. We created 3 architecture configuration. We explain this later. And here we have the number of millions of trainable parameters of each architecture configuration. We start in the TL architecture configuration with something about 11 million trainable parameters, going up to 66.8 millions of trainable parameters. And the maximum is 71.8 million trainable parameters for the wide HasNet network with the TL-E2L architecture configuration. And here we show the number of put features for the output layer in the transfer layer configuration. For training inference, 100 epochs, early stop of regularization with 20%, optimization was mini-batch stochastic gradient descent SCD in the loss of cross entropy. In order to measure the performance of the DNNs, we use the Dataset accuracy measures. To answer the question 2, regarding transfer layer, we defined 3 architecture configurations. The first one, transfer layer, is as-is configuration. We just add an output layer with 2 neurons, one for each class, call it mutant. TL-E1L, we have an extra layer in which we obtained 1,024 elements due to the feature detection and description algorithm oriented fast and rotated brief, ORB. For each image, we get these extra elements. Finally, TL-E2L, we have another extra layer with 256 neurons, the yellow ones, right? All the results in discussion start here. These are the accuracy when submitting the test set. We show all dataset profiles in all architecture configuration. In this column, we have, for instance, the best results in bold HasNet 18 when you consider the TD profile and the TL architecture configuration. But here we have, within the TD profile in all architecture configuration in blue bold, the best performance, which was again due to HasNet 18. The best performance of all was 0.8 in the SS profile, TL-E2L configuration, and using the DenseNet 161 as Oracle procedure. To answer question 1, the overall width of the ranking was DenseNet 161, the deepest network, but in second tier, we have HasNet 18, the network with less layer, and Inception v3. After that, we have HasNet 34, HasNet 50, wide HasNet 50, and HasNet 152. So, to answer question 1, a deeper CNN does not necessarily have better performance than a CNN with less layers. When you use pretended models to address a new problem like we did, it is recommended to eventually start with networks with less layers, which usually have a smaller number of training parameters and usually demand less power of computational infrastructure. For question 2, transfer learning, we compare the performance of the transfer learning architecture configuration with the maximum accuracy between TL-E1L and TL-E2L. Only 2, these here, for red rectangles, out of 40 situations, there is a decrease in the accuracy when we use the extra layers configuration. In all remaining 12 situations, extended architecture resulted in a better accuracy. For instance, in this case here, TL-E1L Inception v3, there was an increase of 36.2% in the accuracy by extending the architecture. Transfer learning is a valuable technique within DNNs, no doubt about this, but eventually we have to extend previous models architectures to get better results. This is our answers to question 2. In order to answer the last 2 questions, we use the Apriori Algorithm association rule, where here we consider the 3 best models, and in the error column, as lower the value, the better. In the correct column, as higher the value, the better. In the profile category, we see that the one dataset support due to some similarity profile is only 60.84% of the current support due to TD in the error column. So we have a substantial increase in the performance just by adding this extra 160 image derived by the test set related codes. Our answer to question 3 is that consider the supervised learning approach and these networks, popular networks, data-centric AI is a promising direction to follow. Finally, to answer the last question, if the software bugs somehow influenced the CNN so that this can explain why they failed, we should see 2 situations in the class category. First, if the bugs influenced, we expected to see a much higher value in the mutant class here compared to the correct class. In the correct column, we might see a much lower value of the mutant class compared to the correct class. We basically see a 50-50 contribution from each class. So our answer to this question is that there is not a clear correlation between the software bugs in the scientific models and the errors presented by the CNNs. To evaluate our technique, FNA, we consider the 3 best models, the entire training set of both profiles, and the 29 corner case images of the test set. 5 of these test images were misclassified by all combinations, 18 combinations of model, dataset profile, and architecture configuration. The remaining 24 images were correctly classified by all combinations. Image features were mean, channel entropy, contrast, dissimilarity, homogeneity, correlation, and angular segment moment. 93 neighbors were defined for the TD profile in 99 for the SS profile. For both profiles, we got the same result. Only 1 image out of the 29 corner case images. Only this image, our technique failed. This provides an accuracy of 0.9655, which is very promising based on the fact that the technique is straightforward. To sum up, the field's techniques related to the study are software testing, test oracle, seed mutation analysis, deep learning, deep convolutional neural network, CNNs, transfer learning, explainable artificial intelligence, data-centric artificial intelligence, data augmentation, image similarity metrics, structure similarity, fresh air inception distance, image features, oriented farce and rotated brief algorithm, k-nearest neighbors, and Apriori algorithm. In the future, we want to address the generalization issues. Of course, we need to consider more types of images in scientific environments, and we want to compare the performance of the FNA technique to metrics such as neural coverage, deep gauge, and surprise adequacy for deep learning systems. We'd like to thank our institute, IMP, and the National Laboratory of Scientific Computation to provide results of this S-Duman supercomputer. This study was developed in the context of the project IDEEP-S. Thank you very much for your attention. And I show here my webpage, GitHub, and LinkedIn if someone desires to be in touch. I'm open to questions. Thank you very much.